Okay. So sorry for that delay, and a little bit about the confusion with this lecture. So the guest lecture's been rescheduled for May 17th, um, which should potentially even fit better because you'll have covered more of the topics before you see how he uses them and sort of what techniques they apply for high content screening. This lecture's quite a bit new and combined with different lectures from last year. And so a lot of the material here doesn't fit into the old slides as well and is being currently updated. So if you downloaded the slides earlier, they're probably out of date. So the name of this lecture, sorry, just to start, will be sort of advanced shape and texture. And the shape, we've sort of covered the introduction to that before. And the texture analysis part is then quite new for this part of the course, and how you can sort of take more advanced analysis of patterns that you see in images and sort of what the best approaches for that today are. So in terms of literature and useful references, the top several sort of stay the same. In particular, what's sort of new for today, the thickness metric and distance map are covered fairly well in this paper. They introduce it with sort of the application to bone and trabecular structure in bone. And so it's very useful for those of you who are working in this field, and it's a very visual example where you can easily understand why these kinds of metrics are important. Then curvature, which we'll talk about briefly, and then finally, that's indented incorrectly, this whole idea of texture and radiomics. Has anyone heard of the term radiomics before? No one. And texture analysis? No? Okay. Well, then I guess this will be a new topic. So in terms of kind of the outline, we'll sort of have the motivation. We'll spend quite a bit of time on distance maps because these are a very useful tool for analyzing different types of images, particularly where standard shape analysis isn't very sufficient. Then sort of thickness maps and what they mean. And then go on to sort of characteristic shapes, some of the curvature ideas, and then texture analysis. So in terms of the learning objectives, what we'll start off with is really how can we measure sizes in complicated objects. And so we saw before that you could quantify anisotropy, you could quantify the bounding box, you could even make sort of the simple inertia tensor, which you could then represent by an ellipsoid. But this doesn't account for a majority of the shapes that we actually encounter on a regular basis. You know, if you're dealing with perfectly round or ellipsoidal cells, that works very well. But as soon as you start dealing with real objects, that becomes much more difficult to use. And so if, you know, even looking at like your chair or your computer monitor, your extents wouldn't tell you very much about that. There are other metrics that you'd want to be able to do. What this then sort of follows into is for those of you with sort of a more chemistry background, when you're looking at processes like diffusion or osmosis in the biological sense, how do you measure the sizes that are relevant for those kinds of processes? You know, they don't care about the extents or bounding box or anisotropy in that sense at all. There's other factors that correlate much more strongly with those kind of chemical or physical processes. Then we'll look sort of a bit at surfaces. How do we examine surfaces in more detail, or interfaces? What sort of techniques are available for that, and how do we deal with them? Sort of complex objects. So how can we analyze complex objects? And are there ways to sort of identify changes in objects as they grow? And so this is sort of a very specific example from fields like rheology, where you have objects that are growing with time, and you want to be able to quantify how the shape changes with time. And so not just the size, which is quite easy with sort of a bounding box, but actually does the shape change. Then for the texture part, sort of how do we quantify patterns inside of images? How can we sort of compare between different patterns? And then sort of the last thing from the medical world, radiologists will often say they'll look at a tumor and it looks evil. And very often, this tumor turns out to be malignant and very problematic. And so how can we take this sort of very nebulous term like looking evil and quantify it in some way? So we'll start off here with sort of distance maps. And a distance map, for the example we'll use here, it's just sort of a perfectly circular object. 1 is the foreground here, 0 is the background. And basically what a distance map is a map or an image of distances. And so each point in the map is the distance that point is from a given feature of interest. So surface of the object, ROI, center of the object. And so there's a number of different ways we can represent this. Right now we'll use surface of the object. And so what this means is for each point inside the object, how far is it away to the boundary between the object, the foreground, and the background. This is kind of the Python or the SciPy definition of this. You can feel free to read in more detail. It has a bit more information on how it's actually implemented in an efficient way. But basically what it looks like when we do this distance transform is we end up, oh, that's so small, with that object where now each point in that object, instead of being foreground or background, is now the distance of that point to the sort of nearest background point. And so here, this is all 1. This is 1.4 because the shortest distance there is sort of the diagonal. And then similarly with 2, you have sort of up to get to the 2. And with 2.2, you sort of have to go over 2, up 1. And so you end up with that distance there. There's sort of a number of different ways this can be computed. We will cover a very, very simple approach. But if you look into these tools more carefully, you'll see that there's these, inside distance transform. There's a number of different implementations. And so we can apply this to our image here, where we see the first one is sort of the exact Euclidean distance transform, and that's EDT. There's the brute force distance transform, which gives us the same results as the exact Euclidean, but is a much less processor-efficient algorithm. And then the Camphor distance transform, which is much quicker at doing these kinds of tasks. And as you'll see, all 3 of these, yeah?
What is the complexity difference between these algorithms?
That I don't know. You'd have to read that in more detail. I think they're all the same order. So if it's a 2D image,
yeah.
I think it's ON squared. The problem is that depending on the shape of your image, you can massively vary. When we get, I'll come back to that in a second. But yeah, so the order is generally you have to go through all the pixels in the image multiple times. But we'll explain why it's not quite that easy in terms of how you actually calculate it. But basically what we see here is that all of them are sort of in the microsecond area, which is quite quick. Probably fast enough that you would never care if you were actually performing this transform for your results. But when you start to look at larger data sets, and so if you go to the Tomcat beamline at the SLS, or you look at full CT data sets in hospitals, or some new MRI techniques, or new light field microscopy techniques, they can make very, very, very large data sets. So one of the measurements you can get at the synchrotron is 2160 by 2560 by 2560. And so clearly this is a point where the speed becomes a lot more relevant. And so if we take a larger image here, where it's 512 by 512, we can then sort of see that the exact Euclidean transform takes 73 milliseconds, but for a SLS scan, it would take 1.1 hours. The brute force algorithm takes around 2 seconds for this 512 by 512 image. And for the SLS scan, it would take 37 hours. And this sort of chamfer distance transform, which we see isn't exact, so it isn't matching that perfectly, this one would take 0.14 hours. And so if you're doing this on large images, you can see that sort of the implementation or how you choose to run the algorithm can first of all affect your results. This is not perfectly circular. So if you were to plot things like isosurfaces on this, it would look very different. This almost looks like a square versus a circle in the first options. And the computational time is massively different. So clearly for getting first experimental results, if you can do something, in 10 minutes, you're much more likely to do it than if it takes you 37 hours. And so how does this actually work? So you start off with your image, divide it into a collection of sort of points in 2 categories. We'll call this foreground and background. We have a sort of distance map operator that transforms the image into the distance map. And so basically for every point in the image, we take the minimum distance to the closest point or to a point in the background. And so basically you have to go through all the points in the background in order to figure out what that minimum distance might be. We use Euclidean distance here, but there's other metrics depending on what kind of data you're dealing with. So if you're dealing with city maps, a Euclidean distance or bird's eye or bird's distance, whatever, line of sight, something like this, won't make sense because you have to drive on roads. And so a distance map that doesn't take into account that you can't just go straight through a building wouldn't be a particularly useful distance map. And so there are ways of doing this with other metrics. And basically, the simple implementation of the distance map looks like this. And so that basically, for every point in your image, you go through this neighborhood, so from -1 to 1. You check to see, if you're at the border. If you're not at the border, then you check to see sort of what the distance is from the point you're at to the nearest point that has a defined distance. And so you run this iteratively until the image stops changing. And so that's one of the problems with defining an algorithm like this is you can say, okay, it's O(n) squared for those of you who sort of a more computer science background. But if this has to run 1,000 iterations and your image is 10 by 10, then the fact it's O(n) squared is fairly irrelevant because it depends a lot on what's actually in the image and how many iterations it takes to converge. So to make this a little bit more tangible, we'll start off with sort of another image like this, a simple block. Why did that not show up? That's good. Speed matter. So here we define the image. And so basically what it looks like is we start off with sort of the first thing we do is set all the points to be the maximum distance we would expect. So all the points in the foreground become 255. Now it's correct. So all the points in the foreground become 255. And then we perform that algorithm where we basically go through each point in the image. And if it's close to a point that's labeled 0, it makes that to the value of the distance to that point. And if it's close to a point that has a distance of sort of not 255, it then adds the distance it is from that current point to the current value. And so you'll see here, as you go through the iterations, the first one here has that as 4.2, and then it realizes actually this distance is shorter in the iteration afterwards, so that you get that final result. But that, if this object is much, much larger or much more complicated, then it can often require many, many iterations to finally come to the sort of converged result. So there's different types of distance maps. The rule we had for the map before was a Euclidean distance. And so each distance is based on sort of the difference of the xy coordinates. So if we go back up here, we see the distance here is the square of the x difference plus the square of the y difference and the square root. And that's what we use as our different distance metric. And so if we change that to something else, we can then get a different map out. And so one of the examples we'll use here is sort of the Manhattan city block distance metric. And so what that is that's sort of the absolute distance rather than having sort of allowing diagonals with this metric. None of the diagonals are allowed, and so basically you have the difference in x plus the difference in y, and if it's 3D, plus the difference in z. And so for the implementation with our very simple approach, all we have to do is change that formula to the absolute distance. Obviously, for the more complicated efficient approaches, this requires much more work to change out that metric because they use a lot of tricks internally to make that work well. Why these didn't load. But that we basically have the same sort of effect we had before, where instead of having floating point distances, we now have sort of integer distances. So each distance is just the number of pixels away, either over or up, that are required to get to that point. And that's how the results look. So in terms of using distance maps in real-world situations, it can be a very useful tool. But one of the critical points that you sort of have to be very aware of is all of these distance maps that we've done so far are calculated in terms of pixels or voxels. And so when we go back to that slide, when we look at that distance, this is not a physical unit, this is a unit of pixels. And so this is 1 pixel away from the border. When we do actual experiments or have real images, that needs to be taken into account. If you're dealing with isotropic images, sort of 1 micron by 1 micron by 1 micron, then it's very easy to convert pixels to, or voxels to distances. Knowing that distance is quite simple. But if you're dealing with anisotropic images, you can't do that anymore. Because if we go back to this image, if each one of these rows, has a different width, you can actually probably even do that. So if we do this, yeah, so here we've sort of artificially made the image taller than it is wide. Unfortunately, you start to see these pixels jamming up together, but that's not important. But basically, this is completely ignorant of that change. So even though we've now said sort of the pixels in y are bigger than the pixels in x, the distance here is still 2. because it hasn't taken that into account at all. And so it's something that when you're dealing with these kind of images, you can't just use them the same way if they're not isotropic in every direction. Otherwise, the distance map won't take that into account. Yeah.
But it's still constant though, so it's not too hard to change it back, or is it? Because here, like each pixel is the same size.
Yeah.
So it wouldn't be too hard to convert, or maybe I'm missing something, but I don't realize really why it's that much of a problem. It would be more if, for example, for me, one part would be smaller, and then the other, and then the scale would get linearly like bigger.
Right. So for that, that's even a bigger problem. That's sort of almost unsolvable.
Yeah.
But when you look at this, if the pixels are taller than they are wide, then the distance here shouldn't be the same as the distance
Yeah,
here.
definitely. Yeah. But can't you just say that? Can't you just take that into account afterwards and correct for that?
No, because you have a 1 here
Mm-hmm.
and you have a 1 there. So we can pause this animation, right? And so if you take it into account afterwards, how do you differentiate between this one, which is actually 1, and this one, which is actually, 1.5?
Mm-hmm. Yeah. No. Okay.
Can you have a correction factor? Just the closer you are to the center, the smaller the correction factor.
You could try that. I mean, obviously with this shape, it's trivial. I mean, it's not very difficult to come up with a distance map, just analytically, where you could then solve directly for what it would be. But as you start to get more complicated shapes, doing that correction after the fact, I mean, you could average, it's 1.1 in one direction and 1.0 in the other. You could just say the average size is 1.05 and you'll be mostly correct. The problem is it doesn't take into account the fact that this is actually further away than that. I mean, so we can go back here. Hopefully this works. So if we say that distances in y are twice as expensive as distances in x, we can do that here. Hopefully this still works. That you'll see that the shape actually, the pattern changes. Because we now have these distances, which are actually coming from sort of the side, versus the ones that are, oh wait, maybe I switched x and y.
Yeah, it seems like.
Yeah, so I switched x and y, so it's actually y is the other one, but fundamentally the idea is exactly the same. That you end up with a different image because those distances have a different meaning. So basically nothing ever comes through here because this distance is too big. That it's much closer to those kinds of objects. And so if you're measuring something, this becomes quite important because if you're trying to figure out, how big is someone's liver, and you're, in medical images, this happens very frequently, where the size of the Z plane, so this axis, is much lower resolution than the others. And so if you were to do a distance map directly on that image, you would have an inaccurate representation and then fundamentally the wrong metrics for assessing that. So you can change that. Probably should get rid of that term. So basically, the solution to this, or the best solution to this by far, is as if part of your filtering and resampling, you convert everything to an isotropic scale. And so if you can take your image and resample it such that the dimensions in X, Y, and Z are the same, you completely get around this problem. Then you can process the images completely normally using the standard functions that are built in. If you can't do that, then you'll have to build your own distance map algorithm if you want to perform that analysis. So often you downsample, because if you were to upsample everything to the highest resolution, you would end up with huge amounts of memory being used, and most of them with not really new information. But depending on your exact problem, it would, if you have plenty of memory and computational time isn't an issue, then you obviously want to upsample. But for most problems, it makes more sense to downsample to sort of the kind of least common denominator, or the biggest axis that you have. So for distance maps, there are two kinds of distance maps that we can make. The first one is kind of the foreground to background, or there's two kinds of distance maps we'll talk about. And this tells us information about the objects in the interior. And so those are the things we started off with, where you have this idea of an object and you want to measure how big it is, sort of using this distance map. You can do the same kind of thing on the background to the foreground. And so instead of looking at the objects themselves, you can look at sort of the distance or the space between objects. So for sort of a boring shape like we had before, you have this ellipse here. You can create the standard distance map where you see this. You can also create sort of the background map where you see that. And so it's just, computationally, it's quite simple. You just take the opposite image as your input. And this tells you then for each point at sort of the surface of the object, how far is it away from that object. So for one object, it's not very interesting at all. But when you start to get multiple objects or more complex shapes, it becomes much more useful to look at this metric. And we also see for this object, it's quite useful because even though if you were to look at this object, it's very large, the largest distance we see is 2. So even though it's a very large object, at no point is any voxel further than 2 pixels away from the boundary. And so that's something we can use to kind of quantify these objects. That if you look at sort of the maximum distance, that will tell you something about the size of the object, and that leads in quite well to what we're doing with thickness maps. So one of the really nice aspects of a distance map is that it's relatively insensitive to small changes in connectivity. And so, if we go back to this tool we covered before of component labeling, there it is. That if we take 2 objects here and sort of have them grow in the y direction. So we have them get bigger and bigger and bigger. On the top, we have sort of the distance map for each one of these sets of objects. And at the bottom, we have the component labeled map. And so what we see in the first image is sort of the histogram of the distances. And so how does that change as these objects get bigger? And then we have here the analysis of the components. And so here we see the number of components and the average area. And so when we quantify this over by sort of the dimension of that axis, we see that if we do connected component labeling, the moment those two touch, our average area explodes. And so if we were trying to quantify what's happening in this experiment or how these objects are growing, this would give us a false impression of how those numbers are changing. Because if you look at this image, it's quite intuitive that the change between sort of this time point and the next one is very small. It's 4 pixels that have moved. And when we look at this curve, it sort of doubles the average area that we get out. And so obviously this is kind of an invented problem, but if you were looking at things like sort of sintering metals or melting objects together, and you were trying to quantify them, this would be very problematic. So if you go from objects that are connected or touching to objects that aren't connected, you get huge changes in your results. And even for experiments where you're looking at sort of cellular imaging, oftentimes cells will be clustered together. And if you were to do a component labeling and then count the number of components you had and look at the average area or the average size of these components, each time you have one of those clustered cells, that would start to skew your results. And so you'd have a very insensitive or hypersensitive metric to something you're not very interested in. And that when we look at sort of the average distance in the distance map, this has a very smooth trend where it's increasing, sometimes slightly faster than other points. I mean, this is a very discrete problem. And so there will be some jumps, but there's nothing like this factor of 2 leap that we have when these two objects start touching. And so if you were trying to quantify it, this would give you a much more stable metric for assessing those kinds of changes. So in terms of real images, so how can we apply this to actual data sets that we have? If we start off with kind of the simple cellular example we've used in a number of lectures before, we have sort of this black and white image. We have sort of these tools to do the thresholding, closing, opening, get a good segmentation out of it. And now once we have that segmentation, we can do a distance map of the foreground and a distance map of the background. And so the distance map of the foreground gives us sort of information, like we mentioned before, about each one of these objects so that we can kind of see how large is it, what's the the long, elongated objects don't have very many high values, and the round, large objects have sort of a more even distribution of values. But the sort of more interesting fact or unit we can extract from this is this ability to see what do the distance between objects look like. And so, we've quantified shape a little bit before, but we've actually never quantified anything like what's the spatial relationships between the objects that we have. Are they kind of clustered together? Are they evenly distributed? And how does that look? And so when we do this distance map of the background, we start to see those kind of trends. And so what objects are very far apart from each other and how we can start to visualize that a little bit better. For the Cortex Mask problem, we can do the same sort of thing. Here, the background doesn't make very much sense. But for the cortex, once we've segmented it, we now can calculate a distance map on this image and start to measure things like what's the average distance to the surface, maybe how big is this object, what's the kind of diameter of this, or what's the average diameter as we go through it. And begin to kind of analyze these sort of results. Boop. And so while it does provide some information, it's not totally obvious how we're supposed to use it clearly. So that, if we go back to that cortical mask, if we take sort of a small chunk out of it and look at all those distance values, we can make a histogram of that. And we can sort of assign some meaning to this top bin where we say, maybe that's the largest diameter that comes up. That's kind of, a reasonable metric for what the thickest point of this object might be. But all these other values don't really tell us very much. There are probably ways we could go about analyzing this in a better way. But fundamentally, it's a pretty difficult thing to extract directly. So besides the maximum distance, there isn't a whole lot we can do with this, which is why we'll get into the the thickness map after the break. Are there questions on the distance map? Things at all?
In the other case, you would also just plot the histogram and see what's the distance between the objects.
Yeah, so if we go back. So if you wanted to quantify the distance between the objects in an image like this, you could plot the histogram and start to look at that. I mean, we can do that quite easily here.
So, for example, the blue area would be reduced if there are a lot of contact points, right?
Yeah.
Instead, if they would be all separated, but then it's difficult to somehow know what does it look like when they're all really far apart from each other, and because there's only one image to compare.
Right. So with one image, it's very difficult to say, I mean, this is what the distance map of that background image looks like. You know, maybe the maximum value is sort of the furthest point between two objects. But you can't do a whole lot with this. Maybe you could fit a curve to it or something along those lines. But that's actually why we get into the thickness map. So the thickness map helps us translate this sort of distance map, which is a more computational approach, into something that has more physical meaning with what we're trying to do. But if you had multiple images and you just compared this distance map of the background image, you could look at that and try to figure out what those differences were. Of course, it doesn't tell you anything about, you know, are they spaced uniformly in one axis and ununiformly in another, or what, where the sort of densest areas are, but it gives you an idea of how far the objects are apart from each other. And so if you were to take kind of local maxima of this image, you know, you could see that these points are very far from the other ones. I mean, so if you were trying to decide where you would put a new Starbucks, you could make a map of the city, a distance map of all the Starbucks locations that you have already, and then find kind of the red areas, and that would be good areas to put a new store, because that's where you're currently very far away from a Starbucks.
And how do you go about to sort of measure the average distance between the Starbucks places?
So to measure, I mean, you could take the average value of that image, and that would say, well, what would the average value of that image tell you? Exactly. So if you take the average value of this image, this is how far you are to the nearest Starbucks on average. And so if you randomly dropped a person in here, how far would they be from a Starbucks? Or if you were looking at how far, you know, if these were blood vessels and you were cells trying to get support, you could use this distance map to sort of assess how far you from the nearest blood vessel, and do cells congregate closer to blood vessels or further away? Are there more regions that are really far away from blood vessels in sick patients or healthy patients? You could do things like that kind of assessment. But for a lot of what we're doing, a distance map alone probably isn't sufficient. You know, for the Starbucks problem, maybe it's interesting to know how far people have to walk on average, but for a lot of other problems, it wouldn't necessarily fit. But it's a very frequently used tool, and it's fairly straightforward to calculate, which is what makes it useful for us. So, if there's no questions, I think we'll take a short break and then move on to the distance.